So, good morning, everyone.
Good morning, sir. Good
Today
morning,
we
sir.
will today we will move to another topic, which is called as transmission control protocol, or we can also write this one as TCP. Okay. In the previous class, we have discussed, right? We are going to have three protocols: TCP, UDP, SCTP. Okay. As we have seen in the previous class, UDP is going to provide us connectionless service, or it is going to provide us best effort service or unreliable service. Okay, and when we consider TCP, it is going to provide us reliable service or guaranteed service or connection oriented service. So first we will try to look at what are the terminology we have, like nomenclature, and try to look at what are the services we have with respect to TCP. Then we will try understanding how TCP is able to provide flow and error control and congestion control. Then we will get into the details of TCP segment. Okay, yesterday we have seen, right, at transport layer we are going to call it as TCP segment or UDP datagram. Okay, and if I consider SCTP, we are going to name that one as chunks. SCTP, SCTP chunks. Okay, so we will look at how a TCP segment is there, like the format and the corresponding fields. Then try to understand how are we going to establish a connection, how we will be maintaining that particular connection, and how to terminate that. Then TCP state transition diagram. In the previous class, we have seen transmission control basic state transition diagram, where we had just listen mode, idle mode, and we had connection established, passive, active connection established. Okay, disconnect, request, receive, all those kind of things. Different terminology we had, right? So this state transition diagram of TCP is going to be like in detail version of how TCP goes from different states to other states, and we'll try to understand timers. We have different timers in TCP. We'll try to understand them. That's about our agenda in TCP. When you look at where TCP lies within a reference model, this particular thing lies in transport layer. Or you can consider, if I consider 5-layer model, we can consider it lies in layer 4 along with the SCTP and UDP. So we have different services offered by TCP. So what are those services? Process to process communication, stream delivery service, full duplex communication, connection oriented service, and reliable service. So what is process to process communication? Yesterday we have seen, if I consider a particular host, source, and another host, destination, delivering from source to destination is taken care by network layer, and within this particular source I'll be running with several processes like Facebook, Gmail, YouTube, WhatsApp, etc. All those kind of things. So delivering to a specific process within a particular host is taken care by this TCP. Stream delivery service. Whenever we are considering this delivery, starting from source process over here until the other end, you are going to have a like a pipeline architecture. Okay, one by one, whatever the segments you are sending, there is some relationship between these segments, and we feel as if we are going to have some stream delivery. Okay, as if like water will be coming through a pipe, right? In the same way, we feel like your segments are traveling through this particular stream. Then full duplex. Full duplex, as you all aware of this term full duplex, communication can happen from server process to client process and client process to server process, or source process to destination process and destination process to source process. And connection oriented, like we are going to establish the connection and terminate the connection before we actually do data transmission. That's the reason we are calling this one as connection oriented service. Reliable, we will be checking. For example, if I am checking, if I am sending 10 segments from source to destination, we will make sure like all 10 segments are received by destination process. Okay, that's how we are trying to provide reliable service. Okay, like how we had UDP port addresses. Similarly, we also have port addresses for TCP. You can see different port addresses. This was there in UDP also. Then we have some things like if you are sending data using a file transfer protocol, then we will be using 20. If I am sending any control information using FTP protocol, then we will be using 21. For terminal network, remote login, etc., we will be using port address 23. For mail transfer, we are using 25, DNS 53. Okay, and bootstrap protocol 67. And this is important, HTTP. We will be using in all web pages, right? We are going to use HTTPS. So the port address corresponding to that is 80. Like that, we have some well-known ports which are defined for TCP. So next thing is stream delivery service. So what is the stream delivery service? Basically, when we consider UDP, we are not establishing any connection. We are not having any relationship between first packet and second packet. Okay, this is very important. When we consider UDP, we are not having any relationship between one packet and the next packet. That means if I consider source is sending 10 packets, 10 datagrams, all 10 datagrams will be treated independently. There is no relationship between first datagram and second datagram. But when I consider TCP, that relationship will be there. That relationship means which comes first, which comes next. Like that, you are going to have relationship for all those 10 packets. Then, in the case of UDP, you are going to preserve message boundaries. Where your message is starting, where your message is ending. That message boundaries are not preserved in TCP. Okay, these are very important. They may ask a difference between TCP and UDP. The first thing you can say is you can talk about UDP provides connectionless, TCP provides connection-oriented service. And when you consider UDP, it is preserving predefined boundaries. Okay, UDP, a process sends messages with predefined boundaries, and you are going to preserve that boundaries till you reach the other side. UDP adds its own header to each of these messages and delivers it to IP for transmission. And each of these messages will be treated as independent datagram. Okay. But when we go with TCP, you are not preserving this message boundaries and you are not treating them independently. You are going to have relationship between first packet and second and third. Like that, you are going to have relationship. Neither IP nor UDP recognizes any relationship between the datagram. That's what I said, right? But when we consider TCP, TCP is going to maintain that relationship. Okay, I hope the concept is clear, the points are clear with respect to connection oriented and connectionless, with respect to preserving message boundaries, with respect to relationship between different datagrams. Okay, and this provides best effort, that provides a guaranteed service. This is unreliable service, that is reliable service. Like that, you can explain the differences. Okay, so when we consider TCP, you are going to have the connection between TCP sending process and TCP receiving process like this. This is the sending process. From here to the other side, a logical connection will be established. And we feel as if whenever the packet is coming, it will be sent through this one. All the packets will be sent through the same stream. But when we consider UDP, it is like you are going to have IP below, right? So each and every datagram may be following different paths. So there is no concept of stream of bytes when we consider UDP. Okay. Sending and receiving buffers. We said like we are using stream of bytes, right? So the sending and receiving processes may not write or read data at the same speed. Okay. So I have source system, I have destination. Let us consider the source is maybe 16 GB and 128-bit processor. It has, okay. The system has this much capacity, and here I have 2 GB RAM, and I can say some 64-bit processor. Okay. So at a time the destination can process 64 bits, but source can process 128 bits, and it has 16 GB RAM and destination has 2 GB RAM. So when the capacity of these two systems are different, there are chances like this may be capable of sending at 100 Mbps per second, okay, but this may be able to receive at 10 Mbps per second. Okay. So it's not possible, right? It cannot receive 100 Mbps per second because it has a capacity of just 10 Mbps per second. Okay. So for example, you have water problem in your area. Okay. Daily in the morning, 6 to 7, some tanker will come and they will pour water and they will go. For example, you don't have any vessels to store the water, you cannot utilize that one. Okay, but if you have some vessels, you can store in them. Okay, maybe tanks, drums, etc. you will use and you will be storing the water. Okay, so because water is coming only at some point of time, you cannot utilize for all services at 6 to 7, you are storing them. Similarly, since my capability of reading the data at this speed I do not have, what I will do is I will try to have some buffers. Okay, whenever the packets are coming, I will try to store in this one, and I will process the data. Storing 100 Mbps per second, but processing 10 Mbps per second. After some time, what happens? Overflow happens here. Okay, the buffers will be overflows. So, for example, you have storage capacity of 1000 liters, 1000 liter tank you have, but they are giving 2000 liters for 2 days. Overflows, right? You cannot utilize after filling that particular thing. So same is the case with this source and destination. Okay. So if source is sending at a faster rate, destination cannot receive and buffers may overflow. Even though you are using buffers, they may be overflowing. Okay. So is it clear the concept of buffers? So it will be like this, sending process, like this colored, pink colored one, when you see, they are the places where I have some data, but I am yet to send that particular data, and this colored portion, I have sent that particular data, but I am waiting for confirmation from the other side that I have received this data. And white colored ones, they are empty buffers. So this is like, it may be like you may be having buffer like 8 bytes something. In reality, it will be 1000 bytes, more than that one. Thousands of bytes you are going to have. I'm going to give numbering 1, 2, 3, 4, okay, 5. So I'll keep on filling. Okay. So it's like first comes first serve, or FIFO model we will be using. So first I will fill in first place, second place, third place, fourth place, fifth place. So first when I process, I will be removing this first place one. Okay. I am going to remove the one in first place one. This one will be removed. Then this one will be removed. But I am keeping. Next packet is coming. After 5, where I have to come? I have to come back to first position. After that, I have to come back to second position. So since we are coming back to the same position again, we are representing like a circular manner. In reality, you are not going to have any buffer in the manner of circles. Okay, there are going to be some space within your memory. That's it. You are not going to have circles, etc. Okay, so just for our understanding, it has been drawn in that particular way. So whenever a byte comes from process, it will be stored here. Okay, and whenever the turn comes, that particular packet will be sent. Okay. At the other side, wherever I have the empty space, I am going to fill that particular empty. And if the process is reading the byte, then the color changes from pink to white. Okay. This is also for our understanding, we are giving these colors. In reality, it will be like you are storing in some memory location. If process reads, that memory location will be freed for storing next byte. Okay. So is it clear so far?
Yes, sir.
Okay. I feel like you do not have any doubts. Next thing is segment. Although buffering handles disparity between the speed of producing and consuming process, we need more steps before we can send data. Okay. It's like continuously keep on sending. We are not going to have any information like where a particular message is starting, where a message is ending, etc. Okay. So the IP layer sends the data in packets, not in stream. So we need to group the data into some format that we are calling as segment. Okay, because you are let us consider we have Ethernet at physical layer. Okay, Ethernet can send 1500 bytes at a time. More than 1500 bytes, it cannot send. If I am keeping on sending in continuous streams, your Ethernet cannot handle that. You need to break down into pieces. Okay. So we consider fragmentation, right? Even before that one, the packets, whatever we are considering, they are going to be divided into segments. And we are going to number them. 1, 2, 3, 4, 5, like that we are going to give some numbering to that one. So you see here, rather than sending continuously, we are going to form segments, and for each segment you are going to attach with respective header, and we will be sending to the other side. Okay. Next we have TCP Futures. So I am just repeating, like we have looked into these things. Process to process delivery, as I discussed, within the host, from one particular process to another host, another process. Source process to destination process, we are going to deliver by taking the help of network layer, data link layer and physical layer. Stream delivery, we have seen the concept. Full duplex, I explained. Connection oriented is complete and reliable service is complete. Okay. So these are the services we have for TCP. They are very, very important. Okay. There can be a question, explain TCP services. Okay, you should be able to answer those things. Then TCP Futures.
No.
And again remember, TCP services are different from TCP Futures. Okay. TCP services means what services TCP is providing. TCP Futures means what features it has. That means to provide that services we are utilizing these features. Okay. To provide services, these are the things we are utilizing. Or we can also say like these are the capabilities we have for TCP. Okay. We have something called as numbering system. Okay. There we will consider different numbers like byte number, sequence number, acknowledgement number. Then we have something called as flow control. We will look into how TCP providing flow control. Then how TCP is providing error control and how TCP is providing congestion control. Okay, so these are the features we have. We will look into the details of these things. So we consider like TCP, we are sending data in terms of bytes. Okay, whatever the connection we establish, the data is being sent in the form of bytes. And we are going to number for these bytes. If I am sending 10 bytes, I am going to give 10 numbers. First byte, second byte, third byte, fourth byte, like that. For all 10 bytes, we are going to give 10 numbers. And the numbering starts with some randomly generated number. Okay, it's not like we are going to start with 0. It has some historical reasons. Like if I am starting with 0, The attacker comes to know like what will be my sequence number. I don't want to give my sequence number like that to an attacker. Okay, we are going to start the sequence number randomly, and from that we will be incrementing that sequence number. So if we are considering like TCP is sending 5000 bytes, and the first byte is numbered with some random number 1001, and each segment if I consider like it is carrying 1000 bytes, then we can consider the segments like this: segment 1, segment 2, segment 3, and so on till segment 5. Sequence numbers will be like this. Okay, here you try to remember, first we consider byte number. Byte number, for each and every byte we are generating from application process of source, we are going to give numbering. Okay, and next thing we are considering is sequence number. So for these 5000 bytes we will have 5000 numbers, but that is different from sequence number. For example, if segment 1 is sending data from 10,001 to 11,000, total 1000 bytes, sequence number will be 10,001. Okay, so segment 2, if it is carrying from 11,001 to 12,000, sequence number will be this one. Segment 3, 12,001 to 13,000, so segment number is 12,001. Segment 4, 13,001 to 14,000, the segment number is 13,001. Segment 5, 14,001 to 15,000, so the segment number is sequence number is 14,001. So what do you understand by looking at this one? What is sequence number? Can anyone say? It's just simple. Look at what do we have? What do we have here? Is there any relationship with sequence number, this particular numbering? Yes, what happened? I don't know why you are feeling difficulty in that. Sequence number is the starting byte of the segment. Is it or not?
Yes, sir.
Then at least like you have to try, even though you are not saying correctly. If you try, it will be good. Okay, at least I will come to know like you are not sleeping. The value in the sequence number field of a segment defines the number of the first data byte contained in the segment. Okay, we have seen in this example, right? So the sequence number is whatever the first data byte we have in the segment, that is considered to be the sequence number. Then we have something called as acknowledgement field. Okay, we define byte number, then we define sequence number, then we have acknowledgement. Okay, I am writing short, acknowledgement number. So in the segment you are going to have a field which talks about acknowledgement. So what is that acknowledgement number is? The next byte the receiver expects to receive. Okay, so to make it clear, we can consider like this: I have sent first segment to the destination, it has received that first segment, then acknowledgement number it will give is 2. Here sequence number will be 1. Okay, acknowledgement number will be 2, because it says like when I receive acknowledgement number 2, it means like I have received till first segment properly, I am expecting second byte. Okay, and we will discuss flow control, error control again in the later topics. Okay, how we are achieving flow control, how we are achieving error control, etc. Okay. So is it clear so far the services and features of TCP?
So,
Yes, tell me.
in TCP services, like we saw the difference between TCP and UDP, no, sir. Uh, Here, I mean, next slide, sir, next one. Yes, sir. Yes, sir. Here they said it will be having header for each of these message, no, sir, in UDP.
Yes.
In next slide or something, you said in TCP also we will be having headers for each packet.
See, header is different from preserving message boundaries.
Okay.
Okay. It's like each and every message you are sending from UDP, you are going to preserve message boundaries there. But in TCP, you are not going to preserve that boundaries. And in TCP, the segments, like I have some data, I may be dividing into different segments. There will be relationship between the segments. Okay, we are not saying like this is complete one message, this is starting and this is ending, like that we are not saying. Okay.
When we are not saying starting and ending, there is no need of header, no, sir, there.
Header has some other information, right?
Okay, sir.
Header also has the information like from which process it is coming, which process to which process it is going. Okay.
Okay, sir.
Okay. So